Hello. This is lesson 9.2, mathematical concepts associated with probability. So we're still sticking with probability, but now we're gonna look at some other concepts. So the first one is the multiplication principle, or it can also be called fundamental counting principle. We use FCP as for it. So if a first experiment can be performed in m distinct ways and a second experiment can be performed in n distinct ways, then the two experiments in that order can be performed m times n ways. So more than one set of things to choose from or more than one set. Okay, let's look at this example. So if the special includes both an appetizer and main course, and there are 3 appetizers and 3 main courses to choose from, how many meal choices are available? So we've got our appetizer 1, we have our appetizer 2, and we have our appetizer 3. Now, with each of these 3 appetizers, we can have a main course, any of the 3 main courses. So main course 1, main course 2, and main course 3. With the second, same thing, we can have all 3 main courses, no restrictions. And the third one, the same thing here. Okay, so we have 3 appetizers. These are the appetizers. And we have 3 main courses. So 3 times 3 gives us a 9. Okay, so this says show organized list. We did the tree diagram for this one, not the organized list. The organized list would be A1, M1, A1, M2, A1, M3, A2, M1, A2, M2, A2, M3, A3, M1, A3, M2, and A3, M3. That would be the organized list. Okay, let's look at the second example. If all the clothes in my suitcase match and I have packed 4 shirts, 2 pairs of pants, and 3 pairs of shoes, how many different outfits can I put together? And here's here's the tree diagram. So we have a shirt. I'm actually going to do it this way. A shirt, a shirt. So 4 shirts, shirt 1, shirt 2, 3, and 4, and 2 pairs of pants. So each shirt can match with pant 1 or pant 2. Now 3 pairs of shoes. So each of these sets can match with all 3 pairs of shoes. So here's shoe 1, shoe 2, and shoe 3. Shoe 1, 2, and 3. Let's see how much room we've got here. 2 and 3, 1, 2, and 3, 1, 2, and 3, and then our last one. So now if we count, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and 24 different outfits. So, but we could just do 4 times 2 times 3. So these are the shirts, pants, and shoes. And we end up getting 24 outfits this way as well. Okay, next one. We've got 2 roads connect cities, A and B, 4 connect B and C, and 5 connect C and D. To drive all cities in order A, B, C, D, how many different routes are possible? So we've got city A and B, and actually, let me do it this way. And there's 2 different routes. B and C, there's 4. And C and D, there's 5. 2, 3, 4, and 5 different roads. So from A to B, we have 2. From B to C, we have 4. And from C to D, we have 5. Now, multiplying these numbers, we get 40 different routes. Okay, next example. We have, so how many different 4-letter radio station call signs can be made if the first letter must be K or W and no letter may be repeated? So no letter may be repeated. So if we think about K or W, we have 2 different options. After that, we have 26 letters in our alphabet. So we've taken one of them because no letter can be repeated. This first one is either K or W that's been taken out already, so we can't use it in the next one. So that means that it would be 25 for the next one. After that, we've taken whatever that letter is. We have 24 left. And for the fourth letter, we've got 23 left. So this would be 26,600 different options. Now, if repeats are allowed, but the first letter still must be K or W. So now we only have the K or W for the first one. The second one, we have 26 options because we have all the letters. Third letter, the same thing, and the fourth letter, since repeats are allowed. Now, when we do this calculation, we get 35,152. Next, if there is no repetition and the last letter must be R, but the first letter still must be K or W. Okay, so we have K or W, so we have 2 options for the first one. The second one, no repetition is allowed. So for that second one, and now there's the difference. Our last letter must be R, so we cannot use R for the second or the third one either. So we only have 24 letters left when this is K or W, and our last letter is going to be R. So we've taken this one and this one out. So that's why 26 minus 2 is 24. Next one would be one less again, 23, and then we're multiplying by the one letter, which is the R. So this is 1,104. So you can see that the options go down quite a bit when we put more restrictions on it. Okay, so next we're going to look at factorial notation. For any natural number n, n factorial looks like this. And by definition now, if we have a 0 factorial, it equals 1. So, for example, if we take 5 factorial, this would be 5 times 4 times 3 times 2 times 1. So we're subtracting 1 from the next one and multiplying them. And we get 120. On the calculator, There is a factorial notation. Um, I don't have my calculator right here with me. Um, but there is a let me grab my calculator so that I'm not saying it totally wrong. Which button? It is on the second row of the calculator, there is PRB. So it's PRB button. When you press it, you have NPR, you have NCR, and then you can see the factorial notation. So you want to take the right arrow to the factorial notation. Now, before you can do it, you have to type in a number. So whatever, so for example, 5, and then press the PRB and then the exclamation mark. Okay, so let's go ahead and look at these examples. So when we calculate 7 factorial minus 3 factorial, 7 factorial is 5040, and 3 factorial, 3 times 2 is 6. So this ends up being 5034. We can put it straight in the calculator as it is. Notice the difference here. This one is 7 minus 3 inside parentheses. So work 7 minus 3 is 4 factorial. That ends up being 4 times 3 times 2 times 1. So 4 times 3 is 12, times 2 is 24. 12 divided by 4 factorial notation. 12 divided by 4 is 3. So this ends up being 3 times 2 times 1, which is 6. Now, there's times when, yes, you can plug it in the calculator and get the answer, but there are some problems where it's gonna give you an error because there's an overflow. Like the numbers are too big. Like I'm looking at this example right here. So, but I'm gonna do this one first to show how we do it. So if we write, so 9 factorial is the same thing as 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And we're dividing it by 6 factorial. 6 times 5 times 4 times 3 times 2 times 1. Now, you can see that we have numbers here that are on the top and the bottom, so we can actually simplify by all of those numbers. And what we end up with is 9 times 8 times 7, which gives us 504. Now, what did we do here? We had 9 times 8 times 7 times 6 factorial and divided by 6 factorial. So notice here, what we used is this one right here. That's where we stopped the top, so that we can cancel these out and get the 9 times 8 times 7. So when we go and do these larger numbers like we've got here, 104 factorial over 102 factorial, what we want to do is we're going to write the 102 factorial here. We're going to stop this at 102 factorial as well. So now these cancel out and we end up with just 104 times 103. Plug it in the calculator and we get 10,712. So a little bit easier. Plus, yes, this would more than likely or can cause an overflow with large numbers on the calculator. Okay, next one is 29 factorial over 24 factorial. So we're going to do the same thing. We're going to write the 29 factorial, the first numbers until we get the 24. 29, 28, 27, 26, 25 times, and I don't have enough room. Let me write it under. 29, 28, 27, 26, 25 times 24 factorial divided by 24 factorial. So these cancel each other out. And then when we do that multiplication, we get 14,250,600. That's a large number as well. Okay, now we're going to go ahead and actually look at what these buttons are on the calculator, the permutation and combination. So permutations, different orderings or arrangements of the R objects are different permutations. So there's the formula how you calculate it. Now, order matters in this one. Whereas you can see in the combination, order does not matter. So each choice or subset of R objects gives one combination. Order within R subjects does not matter. So there's your combination. Now, what we're looking at when we're doing the permutations and combinations, only one set of things to choose from, which will have more options. So which one has more options? When order matters, the permutation, or when it does not matter, the combination. So if we have, think about, we have A first and B next second, or if we have B first or A second. So order matters if A is first or B is first. This gives us two different options, right? Well, when it doesn't matter, it would mean that A, B, and B, E would be the same. So this is 1. So with the permutation, we'll have more options. Okay, listing all possible arrangements of 4 letters A, B, C, and D taken 3 at a time gives you 24 possibilities. What if order doesn't matter? So use different colors to group together the combinations that include the same 3 letters. How many combinations are there? We're going to start with A, B, C. So we have A, B, C here, A, C, B. We've got BAC, BCA, CAB. All of these have the letters ABC, and then we've got CBA. So those are all ABCs. Now, if we look at our next one, A, B, D. So ABD, we have ADB, we have BAD, BDA, DAB, and DBA. Next, we're going to take this next one, ACD. So we've got ADC, CAD, CDA, DAC, and DCA. All of these have the letters ACD, just in a different order. Okay, next combination here is BCD. There's BDC, CBD, CDB, DBC, and DCB. Okay, so what if order doesn't matter? Use different colors. So how many combinations are there? We've got 1, 2, 3, and 4 different combinations if the order does not matter. So what did we just do? If we calculate the combination, our N here would be, we've got 4 different letters. So our N is 4, and our objects, so we've got 4 letters, this is our N, and our objects, so R is 3. So for combination, remember that order does not matter. So we would do 4 and 3. So 4 factorial divided by 4 minus 3 factorial times 3 factorial. So when we do this calculation here, 1 factorial, 3 factorial, we get 4 times 3 factorial divided by 1 times 3 factorial. Those cancel each other out. And we get 4 as our answer. Now, we could, again, plug this in the calculator with the combination button. You would need to put 4, so 4 first, then press the PRB, go to the combination, and then hit enter, and then press 3, and you get 4. Okay, what if order matters? So what's the difference if order matters? So we're going to look at permutations. How many permutations do we have here? So we still have 4 letters, and we pick 3 at a time. Our permutation order matters. Here's the formula. So 4 factorial divided by 4 minus 3 factorial. So 4 factorial divided by 1 factorial, which gives us 24, which is a lot more than what we got when order doesn't matter. And of course, if we count how many we have here, that's the 24 different options. Okay, so remember that it's order, whether order matters or not. Those are the kind of the keywords to watch when we start working on these examples. So the Greek alphabet has 24 letters. How many ways can one name a fraternity using 3 Greek letters with no repetitions? So what do we have here? We have one set. Now, the question is this permutation or a combination? So does the order matter? Yes, the order matters here for sure. Otherwise, it's going to look different. So we are using a permutation. Our N is all the letters, so 24, and we choose 3 of them. So that's our R. So the permutation 24 of 3. We can, again, do this with the calculator, with the PRB button on the second row, second button to the left, and choose the, or actually, before you do this, I'm sorry, you're going to type in 24, then you're going to press the PBR, and then you're going to choose the permutation here, and then enter, and then type in 3. We need that N because it comes before, like it's before the P. That's why it is. Okay, so when we do this calculation, we get 12,144. Next, example 2. How many ways can a merchant with limited space display 4 fabric samples side by side from her collection of 8? So how many choices are there for each consecutive spot? That's what this is asking. So we're going to start with 8. Next one is going to be a 7 because we picked already that 1. Then we subtract 1 from the 7. We've got 6 left, and we've got 5 for the last one. So our in here is going to be the 8. How many are all together? And then R is 4, where we're picking it, or the like how many do we have side by side? We have one set. Does order matter? Yes, order matters in this case. So we're using permutation, and we have 1,680 different options. Now, 4 items are to be randomly selected from the first 25 items on an assembly line in order to determine the defect rate. How many different samples of 4 items can be chosen? So we have 25 items, and we choose 4. Now, randomly selected. So order does not matter in this case. So we're going to use combination. And we get 12,650. Okay, next one is a manager must select 4 employees for a promotion. 12 employees of equal tenure and ability are eligible. So we have 12 and 4 is chosen. Now, since they all are equal, the order does not matter. So that means that we are using the combination, and we get 495. Okay, next one. We have a football team that has 8 juniors and 11 seniors. They need to select a group of 4 co-captains with 2 juniors and 2 seniors. How many different 4-person groups are possible? Okay, so what do we have? We've got 8 juniors and need 2 from them to choose the co-captains. So for juniors, and here, if we look at this, order does not matter. So what we're doing here is we're using a combination where we've got 8 and we're choosing 2. Now, for us to figure out the seniors, it would be we've got 11 total and we're choosing 2. For us to get the answer to this problem, so this would be 28 and this would be 55, is we are multiplying these numbers or these combinations, and we get 1,540 as our answer. So because we have a different, like there's a different amount for um, juniors and seniors, and it's we're picking 2 from juniors and 2 from seniors. So we need them in different grouping. We need to group them separately, instead of just saying that, okay, we've got 19 juniors and seniors and we're picking 4 out of them. We want the 2 from juniors and 2 from seniors. So we have to treat them as 2 different sets. Okay, next question here. From a group of 15 smokers and 21 non-smokers, a researcher wants to randomly select 7 smokers and 6 non-smokers for a study. In how many ways can the study be selected? Okay, again, randomly selected, so order does not matter. So we're using a combination. So we have smokers and non-smokers. And now we're doing this the exact same way we did the football team co-captains. So we are going to separate the smokers. So we have 15 smokers, and we are selecting 7 of them. And then we've got 21 non-smokers altogether and selecting 6 of the non-smokers. So when we do this, we get 349,188,840 different options. All right, next one. How many ways can the letters in the words Fort Worth be arranged? You must divide out the duplicate letters. So what do we have here? And notice, yeah, so the words Fort Worth have 9 letters. So that's going to be 9 factorial. Now, for this one, we can't use a combination or a permutation because we do need to, like it says, divide out the duplicates. So for example, the letter O, we've got 2 of them, so we need 2 factorial. Same thing for R. There's 2 R's on here, and there's 2 T's, so we need to take those into account. Yes, we have an F and a W and an H, but that would just be dividing by 1, so that doesn't really change it. We could put those on here as well, saying 1 factorial for F, and then W, no, W goes down here, 1 factorial, and H would be 1 factorial again. But again, the 1 factorial is 1, so it really doesn't matter. It's not going to change the values. So 9 factorial is 362 and 362,880, and we divide that by 8, and we get 45,360. Now, if you plug this whole thing in the calculator at once, make sure that you put this inside parentheses so that the calculator knows that it's dividing by all those numbers. All right, in how many ways is it possible to answer a 6-question multiple choice test if each question has 4 choices? So this one here, we've got question 1, question 2, question 3, question 4, question 5, and question 6. Each one has 4 choices. So 4 times 4 times 4 times 4 times 4 times 4. This would be 4 to the power of 6, which gives us 4,096. Example 9, a Canadian postal code consists of a string of 6 characters, of which 3 are letters and 3 are digits, which begins with a letter and each letter is followed by a digit. How many Canadian postal codes are possible? So, for example, it can be like G6F, actually yeah, 6F2S9 or something like that. So there's a letter, there's a digit, letter, digit, letter, digit. So there's 26 letters, 10 digits, 26 letters, 10 digits, 26 letters, and 10 digits. We are multiplying all of these, and we get 17,576,000 for that. Now, how many are possible if repetition of letters is not allowed? So our first letter has 26 options. The digit has still 10. Our second letter has 25 options. Digit has 10. And then the third letter has only 24 options because we've taken away and repetition is not allowed. So we get 15,600,000. Okay, that's it for this lesson. Let me know if you've got any questions. Bye.